Hi, I'll talk about using Python for finding roots of equations or to solve implicit equations. I'll also talk about Python codes using Newton Raphson method to solve roots of equations. And Python is a very strong computational language. There are other languages also, MATLAB, Scilab, but I think Python is also really good. And Newton Raphson method is a numerical technique for finding roots of equations using iteration, and it relies on approximation. And it's widely used in science and engineering to solve real-life problems. There are better techniques out there than Newton Raphson method, but Newton Raphson is probably a very simple and one of the oldest techniques. And using it gives you a deep understanding of lateral thinking, how calculus, numerical analysis, and analytical geometry bring everything together. So if you want to learn more about Newton Raphson method, you can check out my other video. I've put a link in the description. And let's make a start. Let's say we want to solve a single non-linear equation. Let's say it's a cubic equation, this one. And we will be using Newton Raphson method, so we write all that down as comments here. I'll write the equation also. Fx is equal to minus x cubed plus 3x squared plus 4x minus 10. Now, there are 4 key steps to this Python code. The first one is you have to define the function and its derivative. So you have to take the derivative of the function yourself and include that in the code for the code to work. And the second step is you have to define the Newton Raphson function along with its arguments, which are initial guess, tolerance between the guess and the next value after the iteration, and the maximum number of iterations. And then you have to provide the initial guess. And the last step will be to call the Newton Raphson function to get the answer. And I think that breaking the code into different steps makes it easy to understand. So let's make a start. I'll define the function, which is basically writing the equation. And then I'll define its derivative. So the derivative of the equation is minus 3x squared plus 6x plus 4. Now I have to define the Newton Raphson function. So I'll give it a name, Newton underscore Raphson, so it's easy for everybody to follow. I can give it any name. I can give it N underscore R, but I think Newton underscore Raphson makes more sense. I'm going to write its arguments. So arguments will be x naught, which will be the initial guess, and then the tolerance, which I think 10 to the power minus 4, 0.0001. I mean, that sort of tolerance should be okay. So that's basically the difference between the guess and the next value you get after the iteration. And then the maximum number of iterations could be 50. You can go up to 60, 70, 100 as well, but I think 50 should be more than enough. And then I'll write xn, which is a variable. So xn is basically any value of x at which the function and its derivative will be calculated. So that's why it's a variable, because this value will change after each iteration. So the first value of xn will be the initial guess, which is x naught. And then I'll define the for loop. So over here, f brackets x underscore n bracket. So this represents the value of the function at point x underscore n. And f underscore xn, that's going to be used in the Newton Raphson equation for iteration, which is why f underscore n is a variable and will change with every iteration. similarly, I will write the derivative, which is f prime underscore xn, and f underscore derivative within brackets x underscore n. So that's the value of the derivative at point x underscore n. Now it may happen that the f prime can be 0. It can happen as well. So, and in that case the Newton Raphson method will not work because the second term will be undefined. The second term in the Newton Raphson formula will be undefined. So I will include a couple of lines here to check against that, so that the code terminates without crashing if the f prime is 0. And it's always good to put comments, so later on when you revisit the code, you know why you have done these kind of things. So I will say that if f prime is equal to 0, then just print that derivative is 0. And we can include another message. Let's say iteration failed, and something like revise the initial guess and return none, because that's not a valid answer. And now I'm going to write the Newton Raphson formula to compute the next step. So based on the formula, that will be x next equals to xn minus fxn, which is the value of function at xn, divided by f prime xn. And this loop will keep going till the convergence is reached, which means that xn and x next, the difference between the two is within the tolerance. So let's write that. If absolute difference, remember we take absolute difference because xn could be greater than or less than x next, so we don't really need negative signs in our difference. So if absolute difference is less than tolerance, then I will say print converge to a root at x, and the value of x will be x next after I plus 1 iteration. So this will give us the value of the root, and this will also tell us how many iterations it took to reach the convergence or reach the root, to find the root or find the solution. Then return x underscore next. And if there's no convergence, if we can't find roots, then we can give a message. We can say that the Newton Raphson method did not converge within the number of iterations. So revise the number of iterations or revise the initial guess. I think this should be good enough. And now we'll give the initial value. So a good initial guess will be, let's say 1.5. Let's start with 1.5 and see what happens. And now finally we will call the Newton Raphson function to get the answers. So we will say root is equal to Newton underscore Raphson, which was the name of the Newton Raphson function, and the argument will be the initial guess, which is in this case 1.5. So this initial guess is basically x naught. X naught will become the initial guess, and the value of initial guess is 1.5. Then we'll just print the message root found, and that will be the root, which will be the answer. I will save the file first before I run it. And this message will be displayed after I run the code if the root is valid. If no root is found, this message will not be displayed. So I will save the file first before proceeding further. Let's try to run it now. Oh, we got an error. Okay, so seems like the equation we put in, we forgot to include the multiplication sign. Let's run it again. Oh, another error. Seems like we missed something. Okay, so maximum iterations. Let's run it again. Oh, says Newton Raphson method did not converge. Why? Let's change number of iterations. Let's increase it to 100. See what happens. Let's increase tolerance to 10 to the power minus 6. Let's see what happens. Same message. Something is not right in our code. Let's try. Over here. How would the code know what to give as an answer? So we need to define. So we need to write x underscore n is equal to x underscore next. So x underscore next is the answer. So we were missing that. So this will be the root, basically x underscore next. Now run it. Okay. Here we go. It says converge to a root at 1.6027 after 3 iterations. Root found 1.6027. So that's good. So we can add a comment that only one root will be found, because this is a cubic equation, because x is raised to the power of 3. So there will be 3 roots, but the method that we have over here in our code gives only one root at one time. We can change the initial guess to see what other values of roots we get, or we can write a code which gives us all the roots of the equations. So I will do that also, but first I will just check with different initial guesses what other roots we get. So let's give it -1. Let's run it. So with -1 we get -1.895 as a root. So that's good. That's the second root of the function. And it took 6 iterations for the code to get that root. Let's give another initial guess and see what happens. Let's give the value of let's give 2.5 as our initial guess. Let's run it. So again -1.895. So I think to find the third root we may have to change the initial guess. Let's give it let's increase it. Let's give it 3.5. Let's see what happens. So yeah, at 3.5 we get 3.292, the third root, after 4 iterations. So there you go, we've got all 3 roots with 3 different initial guesses. So that's good. And if I want to find out all 3 roots at the same time, instead of giving initial guess 3 different times, I can do that by modifying this code slightly. So right now, because this is a cubic equation, x is raised to the power 3, we know that it has 3 roots. So rather than giving initial guesses individually and trying to find the roots, what I can do is I'll copy this code in a new file, and I'll tweak it a bit. So over here, instead of only one root, I will say all 3 roots will be found, and I'll save the file first. everything else remains the same over here. The Newton Raphson function will remain the same. For loop will remain the same. What I need to do is I need to define a function that will run this Newton Raphson function multiple times with multiple initial guesses within the code. So I will define a function that will find all the roots within this code, rather than running the code 3 times. If you run the code once, all roots will be found. So let's say all underscore roots guesses tolerance. These are the arguments, and I think over here and over here I will say roots is equal to brackets, which means that it's an empty list of roots, and whenever a root will be found, it will be stored here and displayed as the answer. The for loop will be root is equal to Newton underscore Raphson guess. So this loop will run the Newton Raphson function first to find one root, and then it will go back to the other initial guess and find the other root, and then it will go back to the third initial guess and it will find the third root. And when the roots are found, they will be stored in that root list. And one thing I've noticed is that because of the computational nature, if you find a root, for example, if you find a root 7.11119, so you've got 6 ones after the decimal and a 9, and you've got another root as 7.1111118, it will consider both of these as separate roots, even though the difference between both roots is 10 to the power minus 7. So to avoid that, I would need to say that round everything up to 6 decimal places. So for example, if you get 3.1111119 and then the other guess finds 3.1111117, it doesn't say that both of these roots are different roots. It will say that both of these roots are a single root, which is why I'm rounding it to 6 decimal places. And now for initial guesses, I will create a list. So this is a cubic equation. What I can do is I can give it 3 initial guesses, but let's say to be on the safe side, I'll give it 4 initial guesses in case 2 initial guesses result in the same root and we end up with only 2 roots. So I want to avoid that, so I will give it 1 initial guess more than the number of roots the equation has. So I'll give it -1, 1.5, 3 and 3.5, and I will just write a comment over here. 4 initial guesses have been listed, which is 1 more than the total number of roots the equation has. And this ensures that no root is accidentally missed. So basically I want to avoid missing a root because of the limitation of initial guesses. over here I will change this to call all roots function to find and print all the roots of the equation. And I will say find underscore roots is equal to all underscore roots with the argument initial guesses, and we have already defined all roots function up there, and then just print the message that roots of the equations are all the roots that have been found. I'll delete this. Let's try to run it. No, we've got an error. This is it should be underscore over here because initial guesses is underscored. Another error. So missing a comma. Now I try and I will run it again. Okay, so we've got all three roots now. Root number 1 minus 1.895 after 6 iterations. Root number 2 1.6 after 3 iterations. Root number 3 3.29 after 4 iterations, and the fourth value, which is 3.29 after 4 iterations. Because we gave 4 initial guesses, we've got 4 answers over there. And then the roots of the equation are in the list. We've only got 3 roots, so this is what I was talking about by giving more initial guesses than the number of roots. So you get everything in one code, or you don't miss any roots. So this is what I was looking for. So that's pretty good. We've got all 3 roots with just one code, and that for loop for all roots did the trick. It ran the Newton Raphson method with one guess, then with the other guess, then with the third guess, and then with the fourth guess, and then compiled everything neatly. So that's pretty good. So this is an easy way of finding all the roots of the equation, and Newton Raphson is a numerical method, so just keep that in mind. There is another way of finding all the roots of the equation without using Newton Raphson method. So Newton Raphson method is a numerical method. Python already has a built-in library called SymPy that uses algebraic method for exact solutions. So SymPy is basically for symbolic computation. It's a computational technique which focuses on algebraic methods to find exact solutions or expressions for roots, as opposed to the numerical method that approximates solutions. So this computational technique involves manipulating the mathematical symbols and formulas rather than relying on numerical approximations. And tools like computer algebra system, Mathematica or Maple, they often use this symbolic computation. An example of algebraic method is finding roots by factoring them. So numerical methods, and Newton Raphson is a numerical method, on the other hand, involves iterative techniques which can approximate roots to a specified degree of accuracy but may not provide exact expressions or exact solutions. Bisection method is another numerical method. So that's the beauty about Python. It already has a built-in library which we can use to find roots without having to code in the Newton Raphson method. Let's try this and compare the results. So I will say root finding using Python SymPy, which is an algebraic method for exact solutions. Again, single non-linear equation. No need to take manual derivative because we're not going to be using Newton Raphson method. We don't need manual derivatives. Cubic function, that's the equation, minus x cubed plus 3x squared plus 4x minus 10, and all roots will be found. So I will import a few things from SymPy. From SymPy I will import symbols, equation, solve, and n. These are really important to solve this equation. And I will define the variable and equations. I will say x is equal to symbols x in bracket, and the equation is minus x cubed plus 3x squared plus 4x minus 10. and this is a symbolic equation. And now I'll try to solve this equation symbolically. So I will say roots is equal to solve equation 0 and x, and then I will print all the roots after the solutions have been found. I will say the roots I will say print the roots of the equation are in some cases roots may comprise of complex numbers, so it will have a real part and an imaginary part. But the way SymPy does calculation in Python is that it always gives an imaginary part, no matter whether you have an imaginary part to the root or not. But the imaginary part is minuscule, so it could be 10 to the power minus 12. For example, the root could be 8 plus imaginary part, and that imaginary part linked to 8 real root would be 10 to the power minus 12 or minus 20. So we want to avoid getting that imaginary part if it's too small. So I will just try to separate the real and the imaginary part over here. So I will say that if imaginary part is less than 10 to the power minus 12, just print real part only. We don't need the imaginary part. And if the imaginary part is not small, is large, then print both real and imaginary part. So basically give answers comprising of both. I will save the file first before running it. Now I've got an error. I'll fix it now. Syntax error. That's what happens when you don't wear your glasses. Can't see properly. Okay, I'll run it again, and there it is. The roots of the equations are, all three roots have been found: 1.6, 3.29 and minus 1.89, and these were the roots that we got with our Newton Raphson code. So Newton Raphson code in Python, we had to code the entire method and run a loop to find the roots. Over here with SymPy, we just have to call that function, and it does the rest for you. You just have to give it the equation. No need to find the derivative and then put the derivative in the code. Just give it the equation and it will solve it itself. And because I only wanted real roots if there were no imaginary roots, so I had to put in a condition that if imaginary roots were less than 10 to the minus 12, don't display them. So I'll make a note over here: all imaginary roots, if they are mathematically 0, will not be shown in the answer. Great. So this is a quick and easy way to find the roots using Python SymPy. Let's change the equation and see what happens. Let's go with 5x cubed minus let's go with 7x squared let's leave it at 4x. Let's change this to plus 15. See what happens if we change the equation. See if we get any imaginary roots or not. Okay, I will change the equation over here also. 5x cubed minus 7x square plus 4x plus 15. Let's run it now. Syntax error. Okay, 5x, so there should be a multiplication symbol over here. 5 multiplied x. Run it again. Okay, so we've got 3 roots, and 2 of them have imaginary parts to it. Okay, so that's great. That's what I wanted to demonstrate. So because in this case the imaginary part is big, 1.3 iota, and 1.3 iota positive negative. That's quite a big imaginary part. So now we want the roots with the imaginary parts over here. But if the imaginary part was really small, if it had been 0.0000000000000 iota or 0.0000000000012 iota, then we would not have wanted that imaginary part. So there you go. This is another quick and easy way to get the roots of the equation, or to solve the equations. That's great. Now what if you want to plot the graph of this function just to visualize it and see how it looks? So we found the answers over here, found the numbers. What if you want to look at the curve of the function? I will save the file first before proceeding further. We can do that as well. So I can add a few lines here so that it gives you the answers along with the graph also. So I will say over here, graph will be plotted. And I will import matplotlib.pyplot as plt. And I will do is I would need to tweak this code slightly, because this equation is a symbolic equation, and what it means is that symbolic equation cannot be used for evaluation purposes in Python. It needs to be converted to a Python function so it can be numerically evaluated. What do I mean by this? So whenever we plot a function, in this case y is equal to 5x cubed minus 7x squared plus 4x plus 15. So we will plot a function by having different values of x, and then we will find out what the y is, and then we will plot those xy points on the graph. You cannot do that if you have a symbolic equation, so you have to convert the symbolic equation to a Python function, which will then be used to input values of x to find values of y, and those values, xy coordinates, will be used to plot the graph. So that's what I'm doing over here, just tweaking it a bit. I'll add the comments, so if I come back to it in future, I remember why I did that. And I try to make comments as detailed and as dumb as possible, because whenever in future you try to open it, you should be able to understand why you did something. And then on graph, what I want is I want the equation to be displayed, or I want the function to be displayed on the graph. So what I will do is I will create a variable which is basically the equation itself, which will be displayed as the title of the graph. So I will say disp, short for display, and then I will type the equation over here, 5x cubed minus 7x squared plus 4x plus 15. And one thing to notice that because this equation has both the real and imaginary parts in its roots, the graph that will be plotted, I want the roots to be displayed on the graph, but imaginary roots are not going to be on the graph, because they're imaginary. So what I want is, I basically want the real part of the roots on the graph. So let's say over here we have 3 roots, 2 of them have imaginary parts in it and 1 is real. So I only that real root will be displayed in the graph and the other 2 imaginary ones will be discarded. So I'll probably tweak the code like I'll say real underscore roots is equal to brackets. So this is where all the real roots will be stored, so that imaginary roots cannot be plotted on the graph. And over here I will tweak this. I will say graph of function along with real roots only. And over here I will add a line of code saying real underscore roots dot append float real part only. So this will add real roots to the list above, which I've written in line number 33. Now I will write a few lines of code to plot the graph. And over here I first need to convert the symbolic equation to a Python function. So xy points for the curve can be calculated, and to do that I will use lambdify, so which I will import from SymPy. So lambdify is a function in SymPy library or SymPy library that converts the symbolic equations to Python functions for evaluation. So I will say f is equal to lambdify, and the arguments will be x equation numpy. So different values of x will be put into the equation to find values of y for the function to be plotted on the graph. I will just add a comment. The lambdify will convert the symbolic equation into the function, so that I don't forget it if I visit this again in future. So now I will give the range for the x-axis and the number of x values that need to be used for plotting the curve. I will say x values np linspace -5 will be the lower bound limit of the x-axis and 5 will be the upper bound limit. You can tweak the limits based on how you want the graph to be plotted. We already know the roots of the equation, so I sort of have an idea about the upper and lower bound limits, but you can tweak around these values. And 500 is the number of x points that will be put into the equation to find the corresponding 500 y points. So xy coordinates, so there will be 500 xy coordinates which will be used to plot the function. You can change it to 1000 also. The more points you have, the smoother the curve will be. The less points you have, the rougher the curve will be. So I want a smooth curve, so 500 seems to do the job for that. So I'll just code the rest of the stuff for plotting the graph. So basically, just an overview. I had to change the symbolic equation to the Python function, and I had to define the equation as a variable so I can include it as a title in my graph. And then I had to write a few lines of code for the function to be plotted. Now let's run it. Oh, we have an error. SymPy import symbols. Oh, it's not lambdify, it's lambdify. I need to wear my glasses. I didn't feel like wearing glasses today. Oh, another error. Pi plot. It should be a dot, not a comma. Okay, now let's run it. Okay, 3 roots found. That's good. Okay, so matplot has no attribute AV. It should be AXV line here, so I must have missed X. Okay, yeah, AXV line. Let's run it again. Hopefully it works. There you go. So we've got 3 roots plus a smooth curve with the title on the graph, and with the root with the red dot, which is the only real root, minus 0.969. If there were 3 real roots, Python would have given 3 real roots plotted on the curve with 3 red points. Oh, something is not right. So the graph title says minus 5x cubed, but it's actually 5x cubed. So over here in display I've added negative before 5, so I'll just remove that. It should be 5x cubed, and there it is, 5x cubed minus 7x squared plus 4x plus 15. That's the title. The legend has the function and the root value. The curve shows the root point as well, so that's good. So that's an easy way of plotting a graph, just to visualize how the function looks like, along with the numbers that you get as your answer. So let's change the equation back to the previous equation that we had, which was minus x cubed plus 3x squared plus 4x minus 10. Let's see what do we get. We should have 3 roots. There you go. So we have 3 roots because all 3 roots were real in that function. So we've got 3 red dots and 3 real roots, 1.6, 3.2 and 1.8, along with the title of the graph. So that's good. That works well. So you can play around with the SymPy, or you can code your own Newton Raphson method and play around with that. I mean, going back to the basics and using Newton Raphson method to find roots and then coding it in just gives you a bit of confidence, and you understand the method a bit more in that way. And hope it helps. Have a great day. Bye.